The next topic we're talking about is zero exponents. So the rule here is if you have any base to the zero, it turns out to be 1. Anything raised to the power of 0 is equal to 1, with the one exception of 0 to 0. That's actually not defined. Okay, so anything other than 0 raised to the power of 0 is equal to 1. So 5 to the 0, well, that's 1. X to the 0, even though you don't know what x is a variable, right? It could be any sort of number. Any number raised to the 0 is 1. How about 10x squared y to the 4th? All of that in parentheses raised to the 0. I don't really care what's in here. Anything raised to the 0 is 1. How about this one? Smiley face to the 0. What does that equal? 1. Okay, anything raised to the 0 is 1. So, I mean, I know that's a little bit of a kind of funny way of thinking about it, but I'm truly trying to get you to understand it doesn't really matter what's in the parentheses. If the parentheses is raised to the 0, then it's equal to 1. Now, this one's a little tricky because the 0 is actually only applied to the thing right before. In this case, the only thing that's right before it is the x. On the ones with parentheses, the parentheses was right before it, so it meant the whole thing, okay? The thing right before the 0 was the parentheses on the second problem, so it meant the whole thing. On this 1, 2, 3, 4, fifth problem here, the only thing that is being raised to the 0 is the x. So 10 stays the same, x to the 0 is 1, and then y to the 4 stays the same, so my answer is just going to be 10 times 1, which is 10, y to the 4. On this next problem, we're testing to make sure you understand what the difference between a negative exponent, a zero exponent, and a positive exponent is. See if you can understand all three of the concepts. So on this first problem, the exponent is not being applied to the negative out in front, so he just stays negative. The 5 to the negative 1, he's not happy where he's living upstairs, so you put him downstairs. Plus, so you put a plus, 5 to the 0. Well, anything to the 0 is just positive 1, and then plus 5. So I have negative 1/5 plus 6, so I need to get a common denominator of 5. So on the first one, I don't really multiply by anything. On the second one, I'm multiplying by 5 over 5, which is 30, which gets me 29/5. Now sometimes people have a hard time with understanding why b to the 0 is equal to 1. So if I just take a moment here, if I have 2 to the 1 and 2 to the 2 and 2 to the 3, you can see that there's a pattern here. 2 to the 1 is 2, 2 squared is 4, 2 cubed, that's 2 times 2 times 2, that's 8, and 2 to the 4 would be 16. Do you see how in each one of these we are multiplying by 2 to get up? Or if you think about it backwards, if you start with 16 to get back to 8, you're dividing by 2. To get from 8 to 4, you're dividing by 2. If you get 4 to 2, you're dividing by 2. If you continue that pattern, 2 to the 0, well, think about in blue. If we were at 2 and we're trying to get back, and we're using our pattern of divide by 2, 2 divided by 2 is 1. That's one anecdotal evidence that a zero exponent is equal to 1. And it goes back even further if you think about your negatives. 2 to the negative 1, well, that's 1 over 2, right? We said that is not happy where they're living, so they need to move downstairs. Well, does that work? If I take 1 and divide it by 2, yep, that's a half. Well, what if I take a half and divide it by 2 to get up here? Well, that's a fourth. Yep, that's 1 over 2 squared, which is a fourth, and the next one will be 1/8. Again, divide by 2. So this pattern works for both negative exponents and zero exponents. So this is just a little anecdotal evidence to see that, hello, that, this pattern does work. It's not that I just made up this rule that anything to the 0 equals 1. It truly does make sense in the pattern. For the next part, we have exponents, properties of monomials. Again, this only works for monomials, one term times a one term. If you ever get into binomials or trinomials, we have to be a little bit careful. But anytime you're talking about one term times a one term, these properties all exist. So for all exponent properties, assume that b is not equal to 0 and m are integers, then these properties are true. So our first property is called the product property, where it says b to the m times b to the n equals b to the m plus n. This is the rule, okay? I first want to show you why the rule works. If I have x cubed, that's x times x times x. Those are all being multiplied because exponents mean repeated multiplication. Then it says times, so I'm going to put a big old black times there. And then in blue, I'm going to do x to the fourth, which means x times x times x times x. But notice the red multiply and the black multiply and the blue multiply are all just multiplies, okay? So I have 3x's being multiplied, multiplying, 4x's being multiplied. So really, a short way of writing this would just be 7x being multiplied. So what is a fast way of doing that to get from x to the 3 times x to the 4 to x to the 7? Well, the fast way of doing it is just to add 3 plus 4. Okay? So that's why the rule works. Let's apply the rule. 5 to the 4 times 5 to the 2. Are the two bases the same? Yes, they are. And what happened when they're the same? They stay the same because we just have more copies of them, okay? Like the x's all stayed the same. Well, in this case, there's 4 5's being multiplied and then 2 more 5's being multiplied. The thing that we're multiplying 5 doesn't change. How many copies of that do we have? Well, 6. 5 to the 6 is a very large number, and I'm not expecting you to multiply that out. If it was a small number, then I would, but 5 times 5 is 25, times another 25 is 125, times another 25 is 625. That's only 4 of them, so this number is going to get really big really fast. Here's another example of why you would really want to know this rule. Could you sit here and write 27 x's out? Sure, I could. Okay, I'm not going to do it. All 27. Times, in red, I'll do 14 x's. That's going to take me a long time. And then do you really want to sit there and count how many x's are there? No way. That is not what we want to do here. What we're going to do is we're just going to keep the x the same and take the 27 and add the 14, which gets me x to the 41. On the next property, we have the power property. The product property and the power property are two rules that people often get confused, which is why I like to have them right beside each other so that you can see how they're different and why they're different. So on this property, it says b to the m raised to the n equals b to the m n. So you have one base and two exponents, and you multiply the exponents. On this first problem, we have x cubed to the fourth. Now let's just kind of work out to make sure that you understand why this works. Anything to the fourth power means write the inside 4 times. So I have x times x times x multiplied by another x times x times x multiplied by another x times x times x and another x times x times x. So we have 4 copies of x cubed. Well, because these are all multiply signs in between all the x's, all of these things are just being multiplied. How many things do we have being multiplied? 12. So the shorthand way to do this, instead of having to write it out every time, is just to take the 3 and the 4 and multiply them. Again, what happens to the x? The x stays the same. So on this problem over here, 2 to the 5 to the 3, we have 2 staying the same, and what happens to the 5 and the 3? They multiply. On the next example, x stays the same, and what do you do with the 3 and the 8? Multiply. So 3 times 8 is 24. So these are our answers, but here's the big kicker. A lot of students will look at these problems up here, underlined in blue, and these problems down here, underlined in red, and they'll get them confused. When do you add? When do you multiply? That's a good question. So what we're going to do is we're going to try to look at the differences between these problems and these problems down here. The first thing students will say is, oh, parentheses, which sounds like it's a good indicator. It's, for the most part, a good indicator, but what if I did x to the 27 times x to the 14 in parentheses? This is the same as our problem down here. So how can you know when to multiply and when to add? The parentheses might not be a very good indicator. The best indicator I have found is count the number of bases. If you have two bases and two exponents, two bases being the same base and two exponents, that means you're going to add the exponents. Notice that the 4 and the 2 on this first example are kind of far away from each other, which means that you're going to add. They have a base in between them. Whereas down here, we had one base and two exponents. So when you have one base and two exponents, you multiply. If you have two bases and two exponents, that's when you add. So that's the biggest difference between power and product property.